So in section 2, we're going to talk about sampling distributions, specifically for proportions. We'll also talk about sampling distributions for means as well, but we're going to start off specifically talking about proportions. So what we're going to start doing is something called statistical inference. So what we're going to be doing is using statistical concepts to interpret scientific results from studies and surveys. So just to review a couple terms, a parameter is a number that describes an aspect of a population. What we're going to be dealing with are statistics, which is a number that is computed from sample data, and it's often used to estimate an unknown parameter. Majority of the time, we're not going to know our parameter. We're just going to know our statistic, and we're going to use that to make inferences about the population. So let's go ahead and take a look at an example. So we have cards from a population of 100. 50% of those cards are pink, and we choose a sample of 10, and only 3 of them end up being pink. So my parameter here, my proportion is 0.5, and my population size is 100. So we use a P to represent our parameter proportion and a capital N to represent our population size. For our statistic, we use P hat to represent that it's a sample, is 0.3, and our sample size, lowercase n, is 10. So a parameter is a fixed number. Now, this was just kind of an example where we knew the entire population, but it's very, very uncommon for us to know that because it's not likely that you can examine an entire population. And then the value of our statistic is known when we have taken a sample, but it can change from sample to sample. So if I put those 10 cards that I drew out back and drew another 10 cards, and I could have found that only one of them was pink, or maybe 6 of them. So multiple samples kind of can result in different statistics. So as we kind of already previously stated, we use a lowercase p to represent a population proportion. Sometimes known, most times not. And then p hat represents our sample proportion, which varies from sample to sample. So kind of going back to that example with the pink cards, if you were to take repeated samples of size 10, the proportion of pink cards should be close to 0.5. So we would expect 5 cards out of the sample of 10 to be pink, but it's not going to be the case every time, and that's referred to as sampling variability. So there's a couple different distributions we can kind of think of in terms of sampling variabilities. The first one is our population distribution. It's our ideal distribution. So in that activity with not activity, but in the example with the pink cards, we know our proportion is 0.5. We know half of them are pink. And then the other half, I didn't specify a color. Let's say blue. So we have that P equals 0.5, which is our proportion of pink cards. Now, a population distribution does not need to be unimodal, which is what we have here. It's the same height. If I had 3 colors, half of them were pink, and then 25% of them were blue, and then 25% of them were red. So population distributions can look different. They don't have to all be the same. So our distributions of sample data refers to the distribution of each individual sample of 10 cards. So for example, the example we looked at for that one, we said our example, we had 0.3 pink, which means 0.7 were blue. If I did it again, I could have had 0.4 and 0.6. So 0.4 were pink and 0.6 were blue. So each individual sample of 10 gets its own distribution. So we have different p-hats. So we have first a p-hat of 0.3, and then we had a p-hat of 0.4, and then you could keep going and keep going. So lots of different sample distributions because it's based on each individual sample of 10. Now, the sampling distribution refers to the entirety of the data. So if I were to do, let's say, 100 trials of this, and I recorded every time, your y-axis would now be a frequency, and I recorded all of the different proportions of pink cards. So now we're only looking at the proportion of pink cards. We're not looking at pink and blue, we're only looking at pink. And you can have 0, 0.1, 0.2, 0.3, 0.4, all the way up to 1, because all of them could have been pink. And then you're just drawing your distributions. So you could add that, and then, so I mean, kind of just of an example here. So the nice thing about sampling distributions is that they should, no matter what, the shape will be approximately normal. Every time. And your center and your spread, so your mean and your standard deviation, should be roughly close. So your mean should be roughly close to the true proportion. It might not be exact, but it'd be very, very close. It might be, instead of 0.5, it might be 0.49 or 0.51, but it'd be very, very close. So what you would do is you take all p-hats from all trials. So let's talk about some characteristics of a sampling distribution. So the first one we're going to talk about is the center and how bias plays a part in that. So when we start taking samples of a population, we have to revisit an earlier question in how trustworthy is a statistic at being an estimate? So is it biased? So a sampling procedure is biased if it tends to systematically overrepresent certain segments of the population and systematically underrepresent others. So in order to avoid biased samples, we want to give every member of the population the same chance of being selected. So we're going to use an SRS for pretty much every type of sampling distribution we're going to look at from here on out. We're going to want an SRS. That way we limit the bias as much as possible. So bias, what it does is it affects the center of our sampling distribution. So our statistic is used to estimate a parameter in an unbiased, a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. So what that means is the mean of our sampling distribution, p hat, has to equal our population p, which we can assume if we've taken an SRS. Next, we're going to look at the spread of our sampling distribution. It has to deal with the size of our sample. So variability comes into play depending on your sample size. So statistics have variability. There's no way around that. But very large samples produce less variability than small samples. So an important fact is that the spread of the sampling distribution does not depend on the size of the population. So a couple ways to think about it is that your variability is described by the spread of your data. The spread is determined by the sampling design, which should be an SRS, and the size of your sample. And the larger the sample, the smaller the spread, which makes sense. So as long as the population is much larger than the sample, at least 10 times larger, then the spread of the sampling distribution is approximately the same for any population size. And the way they came up with this, it's something called the 10% condition. And it states that your sample size n has to be less than or equal to 10% of your population size. Now, we've already kind of discussed the fact that we're not always going to know our population size, but we can kind of guesstimate, oh, it's definitely at least 10 times as big as this. Like if I were going to take if my population were, 18 to 24-year-olds in the United States, and I took a sample of 200, I know there's 10 times that would be 2,000. I know there's at least 2,000 18 to 24-year-olds in America, so I know my sample size is good enough. Now, if I were to take, a sample of 2 million, 10 times that would be 2 billion. I don't know that there's 2 billion 18 to 24-year-olds in the United States. That might get a little bit iffy without doing more research. So when we have met the 10% condition, then we can calculate our spread or our standard deviation. So the standard deviation of a sampling distribution, p hat, is calculated by taking the square root of our sample of our parameter times 1 minus the parameter all over n. And since we've already kind of discussed that, we should not have bias, that means that it's equal to the sample size, or p hat. So let's talk about putting all of these together. So if we were to take all possible samples of the same size from a population and compute the sample proportion, p hat, of each sample, then create a distribution, that's how we get our sampling distribution for p hat. So there are 3 things that we generally look at when we're talking about describing a sampling distribution. We check its shape, its center, and its spread. We're going to talk about a 4th thing, outliers, but it's not really one of the 3 major things we're going to look at. So the first is the shape of our distribution. And the overall shape of the distribution should be approximately normal. We should have a normal distribution. Now, the larger the sample size, the closer the shape is to a normal curve. So this is why we want to take larger sample sizes so we get a normal distribution. So there's a general rule of thumb that we use to determine if a normal curve can be used to approximate the sampling distribution for a proportion. And there's 2 things you have to check. You have to check that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So that means is you have to make sure that you have enough successes and failures. So n times p is your successes, n times 1 minus p is your failures. You want to make sure you have enough of those that you are going to have a normal distribution. So this rule of thumb, or this condition, is called the large counts condition. So as long as this condition is met, we can say that our sampling distribution is normal. Next one is outliers. So this is the one we're not really going to talk about, because the nice thing for us, there's never going to be any outliers or important deviations. So you don't have to worry about outliers. The next one is the center. So the mean, our mu of our p hat, is going to be equal to p. And then again, this is as long as the sample is an SRS. So it has to be unbiased. So as long as you're taking an SRS, the centers of our distribution is equal to the parameter. And then lastly is your spread. So your variability is based on your sample size, not the population size. And the larger the sample size, the smaller the variability. So our standard deviation is the square root of p times 1 minus p all over n, as long as your 10% condition is met, which is the sample size n is less than or equal to 10% of the population. So most of the time, n won't be given. N is going to be described using words because we won't know n. So why we have to do this is because we are going to be sampling without replacement from a finite population. So the observations are not independent because knowing the outcome of one trial helps us predict the outcome of future trials. So because of this, we cannot sample too large a fraction of the population because we're not going to have independence at all for our distributions. So let's take a look at an example. So suppose that 47% of all adult women think they do not get enough time for themselves. An opinion poll interviews 1,025 randomly chosen women and records the sample proportion who feel they don't get enough time for themselves. Find the probability that the random sample of 1,025 women will give a result within 2 percentage points of this true value. Show your work. So what I'm going to do is I'm going to do this very broken down so you can see all of the steps of this process that you have to include. And then we'll start doing this kind of not as broken down. So the first thing you have to do is state the distribution and your value of interest. So what that means is you have to define your P. So in this case, what am I looking at? We're looking at the proportion of women who feel they do not get enough time for themselves. If you don't know what your variable is representing, it's going to make it very hard to do the problem. The next thing we want to do is write our probability statement. So what are we trying to find? So we want to find the probability that we get a result within 2 percentage points of this true value, the true value being 47%. So that means I can be 2 percentage points below, or I could be 2 percentage points above. So I want to find the probability that my sample proportion p hat is between 0.45 and 0.49. So we are always going to use p hat when we're writing our probability statement because we're finding the probability that our sample proportion is within that, not our population. And lastly, just because it's important to identify, we have a P of 0.47 and our N is 1,025. It's very important we know those two things. The next step is to check our conditions and then identify our mean and standard deviation. So there's 3 conditions we have to check. We have to check random. So when we check that it's random, we are checking that we have an SRS. So it does say a random sample was taken. So when we have a random sample taken, that tells me that the mean of my distribution is then equal to my population. So my mean is 0.47. The next thing is that it is independent. So we can't just say it's independent because we know that we're drawing without replacement. So that's my 10% condition. 1,025, which is my sample, has to be less than or equal to 10%, and my population here is all adult women. So if I think 10 times 1,025 is 10,250. Are there at least 10,250 adult women? Yes, there are. So that tells me my standard deviation I can calculate by doing 0.47 times 1 minus 0.47 all over 1,025, and then take the square root. Which is going to give us 0.016. And then the last condition I have to check is it normal? So when I'm checking for normal, two things I have to check: n times p, so 1025 times 0.47 has to be greater than or equal to 10, and n, 1025 times 1 minus p, has to be greater than or equal to 10. So 1025 times 0.47 is 481 point something, so we're good there. And then 1025 times 1 minus 0.47 is 543 point something, so we're good there. So it is approximately normal. So all three of my conditions have been met, which means I can now calculate my probability. So to calculate my probability, I'm going to find two z-scores. So my first z-score, I'm going to take 0.45 minus 0.47 divided by my standard deviation, 0.016. I'm going to get negative 1.25. For my second z-score, we're going to do 0.49 minus 0.47 over 0.016, which is going to give us positive 1.25. So now we're going to go to normal CDF. My lower bound is going to be negative 1.25. My upper bound is going to be positive 1.25. We're going to have a mean of 0 and a standard deviation of 1. And we're going to get 0.7887. Again, you have the other option of here at this step, instead of calculating your two z-scores, do normal CDF with your lower bound being 0.45, your upper bound being 0.49, mean of 0.47, standard deviation of 0.016. Okay. So now my conclusion is going to be a sentence. So the probability that the sample of women have a p-hat within 2 percentage points of the true value is 0.787. So you're answering the question in the context. Your sentence has to be in the context of the problem. You don't want to just write a very generalized sentence. You want to make sure that you're writing it in such a way that someone knows what that probability means, who may or may not be as knowledgeable. All right. So next example, we have that Dane fails to study for his statistics final. It has 100 multiple choice question, each with 5 choices. We're going to assume all questions are independent and that Dane has no choice but to guess randomly on all 100 questions. So for our sample size here, that's going to be 100, because that's how many questions there are. If you have 5 choices, one of them is correct, your probability that you get the answer correct is 0.2, or 1 out of 5. Is the sampling distribution approximately normal? Why or why not? Show your work. So that means we have to do n times p, so 100 times 0.2, and then n times 1 minus p, which is 100 times 0.8. And both of those have to be greater than or equal to 10. And 100 times 0.2 is 20, and 100 times 0.8 is 80. Both of those are greater than or equal to 10, so yes. Is the sampling distribution unbiased? why or why not? If it is unbiased, what is the center of the sampling distribution? So in this case, he is randomly guessing on each question. Which means it is unbiased. So the mean of our sampling distribution is going to be 0.2. And then, do we have to check the 10% condition here? Why or why not? And in this case, we're not actually doing a sample because he's going to answer all 100 questions. So we're not sampling here, which means we don't have to use the 10% condition. We just have to make sure each trial is independent, which we were already told that they were, which is stated. So now that we know it's that it's independent, we can calculate our standard deviation. So our standard deviation of our sampling distribution is the square root of 0.2 times 0.8 all over 100, which is 0.04. So now we've done all that, we want to find the probability that Dane will get at least a 30% on the test. So we want to find the probability that p hat is greater than or equal to 0.3. So let's go ahead and, instead of calculating our z-score here, let's go ahead and use normal CDF with our value. So normal CDF, my lower bound will be 0.3, the upper bound will be 1E99, mean will be 0.2, standard deviation will be 0.04. And we're going to get 0.0062. So it's very unlikely. That is less than 1%. There is a less than 1% chance that Dane gets at least a 30%, which means the more that percent goes up, the smaller the probability becomes. So if I were to change that to passing, it'd be pretty much impossible because that would be a 60% as it continues to go. All right, so for our next example, one way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. So we know that about 12% of American adults are Black, and the proportion of Blacks in an SRS of 1,500 adults should be close to 12% then. It is unlikely to be exactly 12% because of sampling variability. If a national sample only contains 9.2% Blacks, should we suspect the sampling procedure somehow underrepresents Blacks? Show your work using the 4-step process. So when it says using the 4-step process, that means you state your probability and what your variable represents. You then check your 3 conditions. You then calculate the probability, and the last step is to answer the question. So that's what we mean by 4-step. So step 1, P is going to represent our proportion of Blacks. And then we're trying to determine the probability that P hat is less than or equal to 0.092. Now we're going to check our 3 conditions. So we're going to start with random, and it does state in the problem that an SRS was taken, so it is random. Independent, which I'm going to go ahead and abbreviate, just IND. Our sample size, 1,500, has to be less than or equal to 10% of all American adults which there's at least 15,000 of those, so we're good there. And then normal. So 1,500 times 0.2 and 1,500 times 0.8 both have to be greater than or equal to 10. And 1,500 times 0.12, and then 0.88. 1,500 times 0.12 is 180, which is greater than or equal to 10, which means 1,500 times 0.88 is also greater than or equal to 10. So now that all my conditions have been met, I can identify my mean and my standard deviation. So the mean is going to be equal to my population mean, 0.12. My standard deviation, I'm going to do 0.12 times 0.88 over 1,500. We're going to get 0.0084. I'm going to go ahead, instead of calculating my z-score here, I'm just going to go ahead and use my 0.092 and my mean and my standard deviation in normal CDF. So for normal CDF, my lower bound is going to be negative 1E99. My upper bound is going to be 0.092. My mean is going to be 0.12. And my standard deviation is going to be 0.0084. And you're going to get 4.29, a bunch of numbers, and then E negative 4. So that E negative 4, remember, is scientific notation. So it tells me my probability is 0.000 and then 429. So there's a very, very, very small chance that the proportion is less than 0.092. So does this mean that it underrepresents blacks? And yes. So what we're going to say is, since the probability, the proportion of blacks in the sample is so small, we can suspect the sampling procedure underrepresents blacks. So that's what we mean by four-step process. I identified my variable, wrote my probability statement. That's the first step. Second step, I did all three of my conditions and wrote my mean and standard deviation. Third step, I calculated my probability. Fourth step, I wrote my concluding sentence. So next example says a USA Today poll asked a random sample of 1,012 US adults what they do with the milk in the bowl after they have eaten the cereal. Of the respondents, 67% said they drink it. Suppose that 70% of US adults actually drink the cereal milk. So we want to find our mean and standard deviation that says they drink the milk. So it does say it was a random sample, so the mean is going to be 0.7. 1,012 is less than or equal to 10% of all U.S. adults. There's at least 10,000 of those. So for my standard deviation, we're going to do 0.7 times 0.3 over 1,012, all underneath the square root. So we get 0.0144. So explain why you can use the formula for the standard deviation of p in this setting. So 1,012 is less than or equal to 10% of all U.S. adults. So our independent condition has been met. Next, we want to check that we can use our normal approximation for the distribution of p hat. So 1012 times 0.7 has to be greater than or equal to 10, sorry. And then 1012 times 0.3 has to be greater than or equal to 10. So 1012 times 0.7 is 708, which means 1012 times 0.3 is roughly 300, also greater than or equal to 10. So our conditions have been met. Next, we want to find the probability of attaining a sample of 1012 adults in which 67% or fewer say they drink the cereal milk. So we're trying to find the probability p hat is less than or equal to 0.67. So I'm going to go ahead and use normal CDF. My lower bound is going to be negative 1e99. My upper bound is going to be 0.67. I'm going to plug in my mean of 0.7 and my standard deviation of 0.0144. And we're going to get 0.0186. So next one says, what sample size would be required to reduce the standard deviation of the sample proportion to 1/2 of the value you found in part A? So this is a little bit different. So we're saying I want to do half of my standard deviation, so 1/2 of 0.0144. So I want to solve for the sample size that results in that value. So we're going to use 0.7 times 0.3 all over n and then underneath the square root. So we're basically just solving this equation for n. So 1/2 of 0.0144 is 0.0072. 0.7 times 0.3 is 0.21. So now I'm just using algebra. So my first step is going to be to square both sides to get rid of the square root. So we're going to get 0.00005184 equals 0.21 over n. And then we're going to cross multiply. So we're going to put that over 1. Cross multiply, we get 0.00005184 n equals 0.21, and then we're just gonna divide by both sides by 0.00005184. Now, we're going to get a decimal, and we are always going to round up to a whole number, never round down, no matter what that decimal is, because I want to make sure that I have enough so that it is 1/2. If I round down following the rules of rounding, my standard deviation will actually be bigger than 0.0144, and it's okay if it's slightly smaller as long as it's not bigger than what I'm looking for. So in this case, I'm going to get n is 4,051. It's 4,050.9, which is going to become 4,051. Then the last part, find the probability that in a sample of 1,012 adults, between 69 and 71% say they drink cereal milk. So we're trying to find the probability that p hat is between 0.69 and 0.71. So again, I'm just going to use normal CDF with those values and my mean and standard deviation. So lower bound 0.69, upper bound 0.71, mean of 0.7, standard deviation of 0.0144. And we're going to get 0.5126. So let me know if you have any questions regarding the distribution for proportion, whether that's any of the conditions we have to check or any part in the process of calculating a probability.